All right, so our we're warming up here. This is on worksheet 17B, number 7, which you guys tell me is circled, huh? Because I think the assignment for 17 says anything that's got a circle around it. So, number 7. We are gonna go through our yellow chart steps, or yellow card. I think it was yellow for you guys, and it says to first factor everything. So I'm gonna look at this numerator. I notice there's a common x we could take out, which leaves you with x squared plus 3x plus 2 over. And then that denominator factors into, what, x plus 4 times x plus 2? Now, we're not done factoring because look at that numerator. That x squared plus 3x plus 2 is going to factor again into x plus 2 times x plus 1. So I have the luxury of just erasing my work. I mean, you probably do if you have a pencil. It's weird kids do math and pen. All right, so I am calling you a little weird, but that's okay. Let's take a look at our factors, guys. Is there anything that's going to be a removable discontinuity in the next couple steps? I do see one. Do you see it? X plus 2. The factor is going to cancel, which means you're going to have a whole or removable discontinuity at what x value? -2. Thank you. All right. So first question they have for you, though, before you go and cross this off, domain interruptions. So that would be your denominator equal to 0 because anything that gives you a divide by 0 is a domain interruption. So whether it's a whole or a vertical asymptote, it doesn't matter. So for our domain problems, x can't be -2 and x can't be -4. So then I do want to ask you about where the whole is located in this question. And then I heard it's at x. Ooh, that's an at sign. X equals -2. So this is where some of you had a little mess up when you took your no calculator test last week. Some of you had the wrong, like you didn't solve the factor for the whole. That was the first problem. And then when you go to find the y value for the whole, you have to go to what's called the reduced version of your rational. So x times x plus 1 over x plus 4. That's the reduced version. So what happens once you remove the discontinuity? So plugging in a -2 there, you're going to get, let's see, -2 times -2 plus 1 over -2 plus 4. Oh boy. All right, so it's -2 times -1. So that would be +2 over +2, which is a 1. So some of you plugged it back into the original rational, and because it was a discontinuity, you got 0 over 0, and then you're like, oh, 0. Well, gotta be careful about that. Okay, what's next in the list? Is it, I always forget what order this one goes in. Oh, vertical asymptote. All right, so your vertical asymptote would be all the factors that are left in your denominator set equal to 0. And remember, vertical asymptotes are lines. So the line for this discontinuity would be x equals -4. And then it asks you about x-intercepts or zeros. So the zeros would be, again, whatever's left in your numerator set equal to 0. So x equals 0 and x equals -1. However, we always encourage you guys to write ordered pairs as ordered pairs. So 0, 0, and -1, 0. All right, y-intercepts. You can go back to the original version. I think that's the easiest way to find a y-intercept. And if you were to plug in zeros for all of your x's, you get 0 plus 0 plus 0 over 8. So, guys, you get 0 over 8. What is that? That's 0. So y-intercept at 0, 0. So apparently this function goes through the origin. And then they ask me probably about horizontal asymptote next. So back to the original function, I think is the easiest place to look. Is this top heavy, bottom heavy, or equal weight? Top heavy, oh boy. So what does that mean? We don't have a horizontal asymptote, but you do have an oblique. So a little bit of bad news, guys. You are not going to be able to perform synthetic division on this because it's got a trinomial quadratic as a divisor. So you're going to have to do long division. Whew. All right, here we go. X to the third plus 3x squared plus 2x divided by x squared plus 6x plus 8. Okay. x to the third divided by x squared is x. X times the divisor is x to the third plus 6x squared plus 8x. This is the step where some of you messed up last time on the test. This entire quantity is being subtracted, so I encourage you guys to show, I think it's a no-brainer. Put the parentheses down with the negative out in front, and if you do it in another color pen on your test, I think you'll break up your work a little easier and actually remember to do that. So these do cancel. 3 minus 6 is negative 3x squared. 2 minus 8 is negative 6x. So then, boy, need more room. You have to go through all the steps again. So you have a new dividend. So negative 3x squared divided by x squared would be a negative 3. And I'm actually not going to finish the question. Tell me why. I don't need the remainder for an oblique asymptote. So the end behavior equation, or the oblique asymptote, is just the quotient part without the remainder fraction. So it's going to be the line, make sure it's a line, y equals x minus 3. And I'm actually going to stop finishing that question for you. You're going to go ahead and graph all that good stuff. Have fun. Okay. Let's see. I'm going to save that for another day to warm up, guys. All right, this is another warm up. So you can put that worksheet aside. In a minute, while you're digging in your folders, we are going to look at worksheet 14 for our notes. So put that away and get out worksheet 14. All right. So, a little bit of a warm-up here. If I have a polynomial in what we call factored form, you should be able to give me, I mean, it's not going to look pretty, but a pretty decent sketch as far as like what it looks like and some very important attributes of it. So like, for instance, this first one, if it's in factored form, that means that you could clearly identify any x-intercepts. So like, for instance, right here, they're going to have an x-intercept at negative 8. And then right here, you're going to have an x-intercept at 5. So talk to me about what the lead term is for this polynomial. You have a negative 2 times an x times another x. So I don't care about the remaining terms, but what would be negative 2 times x times x? The lead term would be negative 2x squared. So you have, tell me everything you know about this graph. It's a parabola that opens up or opens down? Opens downwards. So the parabola looks like this on the ends. Yeah? I mean, I don't really know how high it goes, and I don't really care for today. But at least I could get a sketch. So like if, for instance, I was trying to match them up to certain graphs, I'd be able to probably deduce my answer from here. So what about this one? Let's start with, tell me all of my x-intercepts. Starting right here. What's this? 0. Very good. So x-intercept at 0. What's this guy? 3. What happens here? Negative 6 with a bounce. Because it's got multiplicity 2. Very good. And then positive 7. Okay, that's a lot of things to think about. Let's talk about our lead term. You have a negative 4 times an x. What do you have here, though? Times an x squared times an x. So what would be, or I said negative 4, didn't I? 4x times x squared times x, which means your lead term is 4x to the 5th. So you have a cousin of a cubic. So one end goes down, one end goes up with a positive coefficient. So the end behavior here, not bad, the end behavior here is going to look like this. Okay, so remember this little star means it bounces. That's the first time it hits the axis, and then it's going to come down. It's going to come across, back over here, and I missed a bunch, but whatever. Okay, so clearly not a good picture, guys. Like, what's new? Even if I had more points, I wouldn't be able to graph a good picture, but we can see that it crosses the x-axis at 0, 3, 7, and then it bounces at -6. So what we're going to have to do today is to investigate a polynomial and determine whether the polynomial has positive outputs or negative outputs. So talk to me about this part right here that I just highlighted in green. Is that function positive or negative in that green part? It's negative. It's below the x-axis. Okay, so I'm not talking about increasing and decreasing behavior. I'm asking whether you're having positive outputs or negative outputs. Today's lesson can be really confusing because there's so many different ways that we could teach you how to do these. So I'm going to show you both methods. One is called using a sign chart, and then there's like the graphing approach. And I'm going to be honest, for me, I prefer the graphing approach, but that's because I'm very strong at graphing. What I like about the graphing approach is it's going to kind of solidify graphing all these polys for you guys. But I will show you both methods. And technically you can kind of use a hybrid method where you use both. So here's what we got going on here. This is in your notes. You have, is this in your notes? Not really. All right, so this is not from your notes, this is from your book. They have this gibberish polynomial that they didn't even tell you the function itself. But they're asking you, where is the function positive versus where is the function negative? And the place where a function switches from positive to negative would be anytime it crosses through the x-axis. So like right here, it's going to switch from positive to negative output. And then right here, it switches back to positive output. And then it switches again to negative output. And then what about here? Because it comes through, is it crossing through the axis there? No, it's bouncing. So while it did hit 0, technically speaking, it didn't come through and create a positive output, so the function is still going to be negative after that. So what they've done is they've created what's called a sign chart. They draw a number line in one dimension, and they mark down all of your critical points. So -4, -2, 2, and 5. And then they wanted you to either put a plus sign or a minus sign, depending on whether your function was positive or negative. So above the x-axis or below the x-axis. And that's what they did. Now, you, from here, should be able to give me a domain interval. So like the function is positive from, let's see. The function is, let's talk about this one, greater than or equal to 0. So right here, and that's it. But did you notice their use of brackets? So at the intercepts, because it said greater than or equal to 0, they used a bracket as opposed to, can you look at the one right above it? When is your function just greater than 0? So why are they using parentheses here? What happens at these points? That is where it crosses the x-axis and it is equal to 0. So the use of parentheses and brackets today is going to be ultra important. All right, this question is already done for you on your notes. Here's what's going on, guys. Today I'm going to give you just polynomials. And you're going to want to use your fancy factoring or sometimes boring factoring and find all of the x-intercepts through factoring. That's the easiest way to do it. Once you have your x-intercepts, what I'm going to have you guys do is draw a sketch, but we're also going to draw a sign chart. As we get more comfortable with these, you guys can probably step away from one part of those approaches. So like you either do a sign chart or you do a graph. If you want to keep doing both, you can. So in this question, they already factored it for you. And we knew this was a quadratic. So then it shouldn't surprise you when you look at this graph from the calculator that at -3 and at 5, those are the places where your function crosses through the x-axis. Those are your x-intercepts. So this part and this part, those are positive outputs for your function, right? I can tell they're positive because they're above the x-axis. Oh, it's 6. Thank you. Good call. 6. Like I said, 6. Okay. All right. This part of the function, which is below the x-axis, is negative. That's what it looks like to be a positive versus a negative function. I know we've been harping at you guys about increasing and decreasing behavior, and I understand why it's confusing now that we're not talking about those. Here we're talking about, do you have positive outputs or negative outputs? Okay, so I like the graphing approach. I would be able to answer this question straight from that graph. Some people like what's called the sign chart approach. So they draw a number line, and they put their critical points on the number line in number line order. So -3 and 6. So if you didn't have this graph, let's pretend we don't have this graph for a minute. What you would do is you'd test values that are on that part of the number line. So like, for instance, give me your favorite number that's on this side of -3. Something easy to plug in, please. Something less than -3. Okay, apparently they went with -4. Yeah. Then what you would have to do is you'd have to plug in -4 into the function. It could be the original function, it could be the factored version of the function, it doesn't matter. But once you plug in x equals -4 and you compute the answer, you find out that the answer is positive. And then I'd have you test something in between -3 and 6. So a really good number to test between -3 and 6 would be to test x equals 0. So again, you'd go to your function and you'd plug it in, either the original or the factored version. But 3 times -6 is a negative number. And then plug in something bigger than 6. So they went with 10. And then they computed it and found out that it was clearly a positive number. So that would be how someone else could come up with the domain intervals for where the function is positive versus negative. Now go back to the actual question, guys. They want to know where this polynomial was. Read that symbol to me. What does that say? Greater than 0. Translate that for me, guys. Greater than 0 means positive. So where is your function positive? So from the sign chart, it would be from -infinity to -3. Uh-oh, do you count -3 or not? No, you do not. And then it's also positive from 6 to infinity. Again, we don't count 6 because it doesn't say equal to 0. This interval would have been the same interval you got off the graph. My personal feeling is the graph is easier for me because I graph really well. That was a joke. I don't graph really well at all. But I can visualize a graph really well because all I need are those X-intercepts. And once I have that and the end behavior, I'm good. I don't like sign charts at all. And here's why. Because you have to do math 1, 2, 3 times. Do you know what you guys mess up on? Plugging numbers in. Which, in theory, shouldn't be that hard for us, right? But on a stressful test, I think we've all done it. Where, like, you know, you write down a 5, it was supposed to be a 6. You plug in something, it's negative, and you write down positive. I don't like sign charts for that reason right there. However, you have to decide which method you like. You could do a combo method if you want. That's what we're going to do, guys. We're going to do a few questions here where I kind of combine the methods or alternate between them. And then you make your own decision, all right? So this one, x squared plus 2x plus 2. Bless Hofbauer Charity graphed it for me. That was nice because I was going to try factoring it, but I noticed that this parabola does not have any real zeros. So this parabola is always living, whoops, up here in positive land. So this parabola is positive through its entire domain. So the question is, when will this polynomial be less than 0? Less than 0 means negative. So you tell me, when is this parabola negative? Never. So how do you want to write that answer? Never. That works for me. I don't want to see no solution symbol. That doesn't really make sense because we're not solving anything. There's no solution to a no solution. So just write the word never. But what if it said, where is this function greater than 0? How do you say everywhere in domain interval? Negative infinity to positive infinity. Very good. All right. This question is not in your notes. Let's, for the sake of time, let's skip to the first one in your notes, okay? I'm going to alternate. On this version, I am going to do this one. Let's do a hybrid method, okay? Now, I'm really excited about factoring. You know I love a good factoring question. So go ahead, try factoring that one. Crickets, crickets. Why are you having crickets on factoring this one? Because you can't. Yeah. this does not have integer zeros. This is going to be irrational, funky, weird quadratic formula zeros. So what I need you to find for me without the use of a calculator are the zeros of this quadratic. So let's do quadratic formula, guys. Negative b plus and minus square root of b squared would be a 9 minus 4 times a times c all over 2a. So you get, what was that, square root of 17? So 3 plus and minus square root of 17 over 2. Now, that's gross. 3 plus square root of 17 over 2 is something positive, and 3 minus square root of 17 over 2 is something negative. I know that because square root of 16 is 4, and this is even bigger than that, so 3 minus 4 would be negative. All right, so here's what I'm going to do. Quadratic has these two x-intercepts. This one is at 3 minus square root of 17 over 2, and this one is at 3 plus square root of 17 over 2. I don't know exactly what the quadratic looks like, except I know it looks kind of like that. That is pretty good, right? Go me. The question is, where is this polynomial? Translate this for me, guys. What does this say? Less than 0. So where is this polynomial negative? Well, it's negative right here. Can you write that for me in an interval, please? I covered up my answer, but where does it start? 3 minus square root of 17 over 2 with a bracket or parenthesis? Parenthesis, because it doesn't say equal to 0. Very good. And then it stops being negative when it hits 3 plus square root of 17 over 2. Oh, lovely. I thought that was pretty close. So that's the graphing method, all right? Let's pretend we never approached the graph. And you would have done what's called a sign chart. So you would have put your two x-intercepts in number line order on the sign chart. So in this case, what I would have had you do is convert them to decimals. So just one of them. I don't need both because I'll be able to tell the difference. Can you guys type 3 plus square root of 17? Hit enter and then divide that by 2 for me and tell me approximately what decimal that is. Did you get it? Saw you type in. Did you get one? What is it? 3 point. All right, I'll go 3.6. So that's roughly 3.6, and that's roughly negative 3.6. So I would have you guys test numbers then. So on the left side of negative 3.6, give me an easy number to plug in that would be less than negative 3.6. That's not easy.
Negative 4.
That's better. All right, test negative 4. So you'd go back up into the original polynomial. Can y'all plug in negative 4 for me? So negative 4 squared is 16 plus 12. And then minus 2. Is that giving you a positive or negative answer? Positive. I don't really care what the answer is as long as I know it's positive. Okay, test something in between negative 3.6 and 3.6. 0 sounds great. So when you plug in a 0, you get 0 minus 0 minus 2. So something negative. And then when you test something bigger than 3.6, what would you like to test? 4. 4 sounds great. I said 4. All right, plus. It's positive. I am boring, but I'm lazy is the overarching adjective there, guys. All right, so that's what a sign chart looks like. For me, the dyslexic teacher, sign charts don't work out great in my brain. So you know what ends up happening? I end up graphing it even after I do a sign chart. So I just kind of skip the middleman. When I answer one of these, I just go straight to the graph. All right. Numero dos. Oh, that one factors. Now, what's going to happen at x equals negative 1? Because I know it's a 0 of the function. but it shows up twice, right? Multiplicity 2. So this quadratic, while it does have a 0 at -1, it's one of those that's going to bounce things. So they want to know where your function is greater than 0. This is a bit of a trick question, because a lot of kids say, oh, well, everywhere it's greater than 0 all the time. Well, that's not really true, because at x equals -1, it is exactly equal to 0. So where is this greater than 0? From -infinity to -1, but you can't count -1 because that's a 0. And then continue on, -1 to infinity. All right, are you okay for me not doing the sign chart on that one? I hate to sway you guys on your approaches, but I'm telling you, just knowing how I know you guys, I think graphing would be better. But yep, the only place that a function would switch from a positive, to a negative would be if it crosses through the x-axis. So that's what we're finding. In calc, you guys call these things critical points. This is just one type of critical point, but so we can't use brackets there because it didn't say greater than or equal to 0. So that's why we had to use a parentheses. All right, number 3. Oh boy. Now, first issue, this is not in standard form. So you're going to have to, whoops, not that. You're going to have to rewrite it in standard form by subtracting the 12 over. And you know I love factoring, but I don't think we're going to have a lot of luck factoring this one, guys. No. I don't think so. No. No, you can't. Right. So here's what we are going to do then. We are going to graph this on our calculator. And on the calculator, the blessed angel Hofbar already gave me screenshots. I don't have to do it, but you guys should. Graph that on the calculator using this standard form of it. And it appears, I mean, if you had to guess, would you say like this is x equals 1? Okay. And then if you had to guess, anyone think they know what's going on here? Is it -3 and -4? Okay. So there's many ways that we could confirm those were all x-intercepts, guys, but the easiest way to confirm them is just to go to your table and look at -4, -3, and 1. So when you guys go to your table, do they show you a y value of 0? Okay. Then we can say, yay, those are the x-intercepts. This is a cubic function, which was supposed to have 3 x-intercepts, up to 3 x-intercepts, and it does. So for me, I would graph it. And it's going to look really ugly. I know it's already graphed here. But I'm going to graph it kind of exaggerated because I need some space to do a little bit of coloring. I'm going to say that this is -4. I'm going to say that this is -3. I'm going to say that this is 1. And we just looked at a picture of it, so let's see if I can mess this up. They want to know where my function is. Translate this for me, guys. What does that say? Greater than 0. So that would be above the x-axis. So we're talking this guy right here and this part right here, which goes forever. So it does not say equal to 0. So my interval right here is going to start at -4, and then it's going to stop at -3. But again, I can't use those endpoints because it doesn't want 0. It just means greater than 0. And then it picks up again at, this was x equals 1, and then it moves on forever. It's going to be positive for the rest of its domain. For the rest of its life, that's right. So if you're a sign chart person, what you would have done is figured out all of your critical points, all of your x-intercepts, which you did on the calculator. Put them down in number line order. And then you would test numbers that are in that part of the number line. So give me your favorite number that you'd like to plug in that is less than -4. -86. Fantastic. Okay. So -86, when you plug that in, you get something negative. Between -4 and -3. Not a lot of choices here, guys, that are nice. So give me something. How about -3.29? And when you plug that in, you get positive. Yes, this is my first hour class, people. All right, in between -3 and 1, a fabulous point to test would be 0. Okay, or 0.2. And you get something negative. And then your favorite number bigger than 1? I can't wait to hear it. What is it? 8,236, or 2. And when you plug in a 2, you get a positive. Okay, have you noticed that they toggled between positive, negative, positive, negative? Is that always going to happen? No, because what if it's got a bounce? Remember that? So a lot of kids go, oh, I just find the first one and then I just toggle them from there. That's very dangerous. You're assuming that there's no multiplicity. And maybe you know there's no multiplicity. And if you do know that, then yes, you can toggle. But be careful. All right, again, this is not in standard form, y'all, so you need to get it in standard form and then hope for the best. So 3x squared plus x minus 2 is less than 0. And this one factors, I think. All right. So what if we do x plus 1 and 3x minus 1? Will that work? No, it won't, Arujo. Because that's a 2. Oh, goodness. I'm done. All right, minus 2. Does that work? 3x minus 2. Okay. So your, quote, critical points, or your x-intercepts, are going to be at x equals 2/3 and x equals -1. So this is where you decide. Do you want to do a sign chart or do you want to do a graph? Totally up to you. Except my teacher keeps saying the wonderfulness that is a graph, but whatever. All right, so this is -1. It's already graphed for me over here, so I'm going to use this graph. And this is 2/3. And remember, we're looking for where this function is less than 0. So that would be, where's your function hanging below the x-axis? So right here. From -1 to 2/3. Talk to me about endpoints. Brackets, parentheses, what you got? Parentheses this time because we're not including the zeros. Very nice. All right. So we're going to stop the lesson there for today. In your bookwork, no, I'm sorry, there's no bookwork today. Can y'all find worksheet 15? And with the time allotted to you here at the end of class, y'all are going to get a great start on worksheet 15. You are assigned numbers 1 through 5. 1 through 5. We will eventually do the rest of the worksheet when we learn the rest of the lesson. But please, 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 1 through 5. And you guys have, oh my gosh, 6 whole minutes. You can probably get like 1 through 3 done.
Yeah, looking like